of the occupants. So normally they are very compact, so a lot of occupants will be there in the population density will be very high in a typical aircraft, and everybody will be releasing heat, okay, due to metabolic rate and all. So there is large heat generation in a small volume, right. So this will add to the sensible and latent heats of the system, okay. So as a result temperature and moisture content will increase. Apart from the occupants, you can also have in fact you will also have a large amount of equipment which will be releasing heat, okay, many electronic controls, motors, etc. Okay, all these equipment will be releasing heat continuously. So you have continuous heat addition to the air inside the cabin because of the people and equipment, okay. So if you and this will not this will be much more compared to the heat transfer from the cabin to the outside, okay. So if you do not provide any cooling system, because the internal heat generation temperature can shoot up. This is not the only reason, you also require cooling because there will be heat generation due to skin friction. Typically aircraft will be moving at very high speed, okay. So when it is moving at very high speed in an air, there will be large relative velocity, okay. So the boundary layers will develop on the surface, okay, and since air has a finite viscosity, as you have seen in the earlier classes, there will be frictional losses, and because of the skin friction temperature rises, okay. The temperature of the body, outside body, will be higher because of the skin friction. So there will be actually heat transfer from the surface of the body to the interior because of the skin friction, okay. So this is the second reason why you need a cooling system. The third reason is the ram effect. So because of the ram effect also the temperature of the air increases, okay. So I will explain the ram effect in a little while. And the fourth effect is solar radiation. For example, if the aircraft is flying during the daytime, then there can be considerable solar radiation, and because of solar radiation the temperature can go up. So these are the four reasons why we need a cooling system, okay. Typically if the aircraft is flying at low altitudes, at low velocities, then maybe you can do away with the air conditioning system, but if it is flying at high speeds and at high altitudes, an air conditioning system is a must. Now air cycle refrigerant systems are preferred in aircraft. So why do we use air cycle refrigerant systems in aircraft? Because of the following reasons. The first reason is that obvious reason, air is cheap, non-toxic and non-flammable, okay. Typically you do not want to use any explosive or flammable gas in an aircraft, okay. It has to be absolutely safe. So air is the safest refrigerant that you can think of. It is easily available, it is non-toxic and non-flammable, okay. So this is one of the main reasons why we use air in aircraft refrigeration, okay. The second reason is the leakage of air is not a problem. So leakage of air from the system is not a big problem. And an open system can be employed eliminating cold heat exchangers. As I was mentioning just now, if you are using air, you can have an open system, that means you can directly release the air into the system, you need not have a cold heat exchanger. What is the advantage of not having a cold heat exchanger? As I have mentioned, the system weight will be reduced considerably. When you are designing an air conditioning system for aircraft, the most important criteria is the weight per kilowatt, okay. So the weight is a very important factor, and the volume is also of course an important factor. The system that you choose must be lighter, okay. So you will see that for aircraft air conditioning the air cycle systems will be lighter, okay. One reason is you do not really require a low temperature heat exchanger, okay. And the fourth reason is main compressor of the aircraft itself can be used for compression, okay. A typical aircraft engine already has a compressor, okay. So you also need a compressor for the air conditioning system, okay. So if you are using air cycle refrigeration for air conditioning, you can use the main compressor of the engine itself for compression of the air, okay. You do not require a separate compressor. So you can see that you do not require a low temperature heat exchanger, and you also do not require a separate compressor. So this will lead to significant reduction in the weight, okay. So you will find that weight per kilowatt of an air cycle system will be much lower than a comparable vapor compression system, for example using a reciprocating compressor. In fact, the calculations show that the weight will be typically 50% that of the comparable vapor compression refrigerant systems, okay. So this is the these are the reasons why we use air cycle refrigerant systems in aircraft. Of course, the last reason is that the design of these systems are considerably simpler and the maintenance is also easy, okay. So these are the reasons why we prefer air cycle systems in aircraft. Now there are different types of systems used in different situations and for different types of aircrafts. Okay, for example, you can have what is known as a simple system, you can have a bootstrap system, you can have regenerative system, you can also have what is known as a reduced temperature system. Okay, there are other systems also. Okay, these are the three main systems. The fourth one, as I said, is reduced ambient system. Okay, so each one has its own advantages and disadvantages and applications. Okay, let us quickly look at these systems. The first one is what is known as simple aircraft refrigeration system or a simple system. This is an open system. The power, okay, let me first explain the cycle. Okay. So let me begin at point 2. Okay, and let us look at the TS diagram first. Okay, so this point 1 is the ambient air. Okay, so ambient air, the pressure and temperature of the ambient air are increased due to ram effect. Okay, process 1 to 2 is what is known as the ramming process. Okay, during the ramming process, its pressure and temperature increases. Okay, so what we have basically at point 2 is ram air. Okay, so ram air goes to the main compressor. Okay, MC is the main compressor of your aircraft engine, right? So it goes to the main compressor, it gets compressed from process 2 to 3. Okay, so a part of the compressed air goes to your engine and a part of it goes to the air conditioning system. Okay, so at point 3, the air that is used for air conditioning system enters into an air cooler, AC. Okay, AC is the air cooler. And how do we cool this air here? We again use the ram air for cooling this air. You can see that temperature at point 3 is much higher than the temperature at point 2. So you can use the ram air for cooling this air. Okay. So the process 3-4 is what occurs in the after cooler. The temperature decreases almost isobarically from 3 to 4. Okay, and ram air is used for cooling this. And at this point, at point 4, it enters into the cooling turbine T. Okay, and it undergoes expansion process 4 to 5. And as you know, at this point, you have a very cold air. Okay, at point 5. So cold air at point 5 is released into the cabin directly. So okay, so this air goes to the cabin, and in the cabin it picks up heat, and by the time it comes out of the cabin, its condition will be at point I. Okay, so process 5 to I is what has happened in the cabin, right? And the power output of the turbine here is not used for running the compressor or anything. It is used for running a fan. Okay, so what does this fan do? This fan drives the air through the after cooler. Okay, so that means the power output of the turbine is used for running the fan, and the fan makes sure that sufficient air flows through the air cooler continuously. Okay, so this is what is known as simple system, and here you can see that I have shown the actual cycle. So you have some pressure drops here and non-isentropic processes also. So what is the refrigeration capacity of this system? Refrigeration capacity of this system is nothing but m dot Cp into Ti minus T5, where Ti is the cabin temperature. Okay. Now let me explain the ram effect. Ram effect is the pressure and temperature of the outside air increases as it comes in contact with the aircraft due to the conversion of kinetic energy into enthalpy. See, air may be still, but the aircraft will be moving at very high speed, so there will be large relative velocity between the air and the aircraft. Okay, so when the air comes in contact with the high relative velocity air comes in contact with the aircraft, its kinetic energy will be converted into enthalpy. Okay, so the ultimately you have the enthalpy being converted into temperature and pressure. Okay, so you have, because during this process the kinetic energy is converted finally into pressure and temperature. Okay, so this process is known as ram process or ram effect. Okay, and you can very easily show that the temperature rise during ram effect is given by this relation. Okay, T2 dash by T1. T2 dash is the temperature at the exit of the ram process, T1 is the temperature of the ambient. Okay, this is equal to 1 plus gamma minus 1 by 2 into m square. Okay, where m is nothing but a Mach number. Okay, if you remember, the Mach number is defined as the ratio of the velocity of the aircraft divided by the sonic velocity. So, A is the sonic velocity, right, and sonic velocity, as you know, is for an ideal gas is equal to square root of gamma into R into T1, okay. And the ram efficiency, because the ram process is not strictly isentropic, you can define a ram efficiency as the actual pressure rise, this is the actual pressure rise, and the pressure rise if the process is isentropic. Okay, so we have the ram temperature rise during the ramming and the pressure rise during the ram process. Okay. So, as you can see that the power output of the cooling turbine is used for running the fan, and this system is suitable for ground cooling. Why is it suitable for ground cooling? Because on the ground you do not have the ram effect, okay, because of the ram effect always there will be airflow on the air cooler as long as it is moving, but on the ground the aircraft is grounded, so but still the fan can drive the air, okay. So, this system is generally suitable for ground cooling, and this system is suitable for low speed, low altitude aircraft, okay. So, simple systems are used for low speed and low altitude aircraft. The second system is what is known as a bootstrap system. Let me very quickly explain the bootstrap system. In the bootstrap system, we have two heat exchangers and an auxiliary compressor. So, the ram air gets compressed in the main compressor MC, and at this point it enters into the air cooler. So, 0.3 to 4 temperature reduces, and at 0.4 again it is compressed in an auxiliary compressor from 0.4 to 5, okay. So, the 0.4 to 5 is what happens in a auxiliary compressor, okay, and at 0.5 again it gets cooled as it flows through the air cooler 2, okay. So, during this process again the temperature drops from 5 to 6, and at this point it enters into the turbine and it undergoes the expansion, and at this point it goes to the cabin. Okay, so you can see the difference between the simple system and the bootstrap system, okay, and here the power output of the turbine is used for running the compressor, right, and the ram air is used for cooling the air cooler 1 and air cooler 2, because the same ram air is used, right. So, obviously you can see that this system is not really good for ground cooling, because when it is on ground you do not have any ram air, so the air coolers cannot be cooled. So, normally you do not use this system for ground cooling, you normally use it for high speed, high altitude flights. So, as I said, suitable for high speed aircraft flying at high altitude, it uses two compressors, two heat exchangers, and not suitable for ground cooling. The other system is what is known as regenerative system. I will not explain this system, but I will just tell the briefly. In a regenerative system, a part of the cold air from cooling turbine is used for pre-cooling the air entering the turbine. That means what is done is you take some cold air from the cooling turbine and use the same cold air for pre-cooling the air, okay. So, that means the air entering into the turbine will be pre-cooled, okay. So, the advantage of this is that exit temperature of the turbine will be very cold, okay. So, in a typical regenerative system you can get very cold air, okay. Of course, this is at the cost of increased weight and design complexity. And one last thing is all the different aircraft cooling systems are compared based on an index called dry air rated temperature, or DART, okay. DART stands for dry air rated temperature. It is defined as the temperature of air at the exit of the cooling turbine in the absence of any moisture condensation, okay. That means when the air is very dry and as it undergoes expansion, there should not be any moisture condensation, okay. Under such cases, what is the temperature at the exit of the turbine? That is called as dry air rated temperature, okay, and this is the index used for comparing different systems. And normally the aircraft systems are rated based on the mass flow rate of air, okay. So, the rating is done based on the mass flow rate of air, and the refrigeration capacity is obviously given by a mass flow rate of air m dot into Cp into Ti minus DART, design DART, that means design dry air rated temperature, and Ti is the cabin temperature, and m dot is the mass flow rate of the air, okay. And a comparison of different aircraft refrigerant systems based on DART at different Mach numbers shows that DART increases monotonically for all systems except reduced ambient system, and simple system is good at low Mach numbers, and at high Mach numbers we have to use either bootstrap system or regenerative system, and the reduced ambient system is generally good for supersonic aircraft. Okay, let me quickly conclude what we have learned in this particular lecture. We have discussed the reverse Carnot cycle and its limitations, and we have discussed ideal and actual reverse Brayton cycles, and we have looked at various aircraft refrigerant cycles, and we have also seen the concept of dry air rated temperature. And as I mentioned, the performance of all the above systems can be obtained very easily using the basic thermodynamic concepts which we have discussed in the earlier lessons and also in this particular lesson. Okay, right, thank you.